Time to market is critical for any successful product to launch. Nowadays, it's common to reuse portions of known circuitry in order to focus on developing new technology while saving time by leveraging known good circuits where possible. Utilizing reference designs is a quick and easy way to repurpose verified circuitry and expedite your design process. This intellectual property often comes directly from manufacturers, but the likelihood of matching exactly with your design specifications is slim. Understanding why design decisions were made will help you adapt reference designs to meet your needs and save precious design time. In this video, we will perform a design review of a MAXIM integrated reference design. We'll determine which design decisions are important, why they were made, and what to look out for when incorporating this circuitry into a new design. Before we even look at the printed circuit board, we need to understand the design itself. When I'm looking at a schematic for the first time, it can be overwhelming sometimes. Every designer has a certain way of doing things, so deciphering the design intent may not be straightforward. Well, I use what I call the input process output method, or IPO method for short, to understand any schematic design. First, I learn all the inputs, things that process information internally, then functions that create outputs. Input, process, output. Then I block off entire sections of the design that support these major input, process, output functions. Only after I understand the functions and what roles they play in the inputs, processing, and outputs do I get into more details. I'll demonstrate this method in this design. Let's look at inputs. The primary input and function to any design is power. Why power first? Well, every printed circuit board needs power to make the PCB work. If power fails, then so does everything else. So I always start with power. Here we have the PMIC, or Power Management Integrated IC. The capacitors need to be close to the integrated circuit. Just below, we have the power section of the microcontroller unit, intentionally separated from the control section of the chip. Let's see if there are any other possible power devices like the USB powered areas. Alright, sure enough, the USB-C protocol is used here for also getting power into this device. Once I've found all power sections of the design, I look for another input function, and that is communication from the outside world. That would typically be some serial input device, debug pins, touchscreens, sensors, and so on. In this board, we have serial communication from the USB device. So that's another input. It also has SWD, or serial wire debug, so that we can debug and test the board after it's been manufactured. Now, what else do we have for input communication? We have the internal measurement unit, or IMU, which is the accelerometer. This detects force, motion, acceleration, and similar kinds of movement and position. These are inputs coming from the outside world, and that's why I grouped it in this section. So our input sections are complete for this design. All right, after understanding inputs to the PCB, I look for how that data is processed. Usually it's a main controller, processor, or some other processing device. Let's circle back to the main processor, which handled most tasks in the design, using as much input power as needed to process as much data as possible. So we see the main input at the top. That is power. And if we scroll down, we see the main CPU, or the main communication or processing section of the CPU that takes the inputs from the other devices. Now, oftentimes, a design has more than one processor to support the main processor. That would be this NAND flash memory, which can have communication with memory directly. With this second device, the main processor can have more freedom to focus on other tasks because this can process the memory directly. Alright, it looks like we are done with processing. The final step in my IPO method is looking for outputs. So let's look for anything that outputs anything, such as information or signals or indication. First, we have the BLE or Bluetooth Low Energy module. This sends signals and information out to other devices. A perfect example would be like a cell phone in this case. Just a quick side note, why use Bluetooth Low Energy? Well, this watch is going to operate off a battery a lot of the time. So we want a lower energy consumption to assist the user during a brisk run or a 5K or some other task that's going to take a few hours sometimes. We also have the tricolor LED, which sends signals to the outside world, just making sure that we see what's happening. So I categorize that as an output. Finally, we have the sensor board connector over here. It's supposed to connect externally to the sensor board that's a separate PCB from this main board. Okay, so that covers all of our outputs. Using this method helps me to understand nearly any schematic, whether disorganized like a lot of designs I've come across, or if they're blocked out nicely like this one. Okay, now that we understand the purpose of each section in the design, we are ready to review the printed circuit board. Let's look at the completed board using 3D modeling for a realistic representation of the design. There are so many things I can talk about here, but first, let's handle the most important section that everything else relies on, which is power. For power delivery, they place the power traces and regulation chips in the center of the board near the top. Why is that? Because it's close to all major parts, such as the Bluetooth module, any voltage regulators, and it's a bit further from the MCU, but it's not all the way across from the printed circuit board. A somewhat centralized approach is ideal for many PCB layouts for power, as that reduces inductive loops on all traces or areas, therefore reducing the impedance of any given power trace. Reduced impedance on those power traces means that you'll get a lower voltage drop across that trace when current flows through it. And maintaining your voltages is very important when it comes to power. Now, let's look at the Bluetooth module. This is a critical component whose placement should take priority. That's because the datasheet gives firm guidelines on how to place the module. Also, the placement of the Bluetooth module will have a direct effect on the placement of the remainder of the components. So when placing Bluetooth devices, pay special attention to the datasheet since it saves a lot of time from trying to figure out how to place the module on your own, especially for RF and power electronics. According to the Bluetooth module datasheet, ideally we would go in the center right side of the PCB. That's where it would go. But this placement is fine actually. Next, we also have the USB-C, which is located at the edge of the PCB. This makes sense as in general, you want devices that need a physical connection to the outside world to be easily accessible. So you would place connectors on the edge of the PCB. Also, we won't have to open the watch case, which is somewhat transparent here. If I click on it, this is the case. We won't need to open it up in order to put power into the USB port. All right, so that's mostly it for component placement, and we will move on to the individual signal layers of this printed circuit board. Let's examine this design layer by layer to determine the important design decisions and why they were made. First, let's look at the outer layers of the board. We are looking at the top copper layer. You want to route as many traces to ground reference as possible, especially on chips. And see, Each of these capacitors, we have a route to ground as short as possible. These are called fanouts. Why would we do this? Because that greatly reduces the inducted loop from any pin to its return path to ground. Minimal loop inductance causes minimal impedance, then a lower chance of issues for any given chip or device or PCB. Also, where possible, try to route as many return vias as you can to ground. For instance, here we have some return vias that go to ground, and this is just a via that goes to ground, but it's next to a 1.8 volt trace or an analog input trace. The reason for that is we have some EMI that can be reduced by having a direct path or nearby path to ground. This technique can help reduce crosstalk for free. Now, I'd like you to notice how there are different widths for all these traces. There are multiple reasons for this. The traces that carry high-speed signals must have a certain or specific impedance. So the wider their width, the lower their impedance, and the narrower they are, the higher their impedance. And so we need to use specific widths for those traces. Thickness also plays a factor in trace impedance. But that's for high speed. What about these wider traces on the voltage rail, for instance? For traces which don't require a specific impedance, such as the ones delivering power, they need to be wide enough to carry higher amounts of current than the other traces. For the remaining traces, they need to be narrow enough to allow adequate space to route all the other traces, but not so narrow that it would be cost prohibitive or where it may be impractical to make a trace that narrow. Now, it's always great to have as wide a trace as possible except on two occasions. One, when the trace is the switching node of a switched mode power supply. You only need it as wide as it has to be to carry the current. Don't make it any wider or you may start causing EMI issues for your switch mode power supply. So that's a very specific case. The second occasion is when a trace needs to have a certain impedance. Otherwise, if you're not dealing with those two situations, feel free to take advantage of any available space to lower your conductor impedance. However, remember the trade-off of getting as many routing or signal traces as you can into any area of the PCB. So it's really a lot of trade-offs when it comes to routing and trace width. The most common concern and question I get is how wide do I make the trace? And you can just use a calculator for that. But the main thing is you make your trace as wide as it needs to carry the current. Make sure that's always the case. Now, in some situations, you might have instructions from the data sheet that want a wide trace, but not because of current. For example, for the power conversion chip, the MAX20303 BEWN, that's a lot to say, sys_out got routed to a wider trace. But this signal does not carry a lot of current. So why make the trace any wider than it needs to be for carrying current? Well, according to this part's datasheet, this trace needs to connect to a low impedance trace. Having a wider trace lowers its impedance. So that's why sysout gets connected to this wider trace. And if we turn on layer 3, also notice how the engineer made the trace wider on the inner layer signal trace and on the top layer. All right, I think we covered enough in general about the top upper layer. So let's move on. Next, we move to the ground reference layer. The overall strategy for any voltage reference plane is to retain as much copper as possible so that the plane has as low an impedance profile as possible. Why do we care about impedance being low on the reference plane? Because the net on that plane serves as a reference point for all other signals and devices. If the plane has noise and voltage fluctuations, it starts to become a poor reference. That means we can't trust 0 volts reference is actually 0 volts reference, typically called ground. It could be 5 millivolts, it could be 500 millivolts, 200 millivolts. So we don't want that to happen. So with that in mind, let's see how the engineers utilize the zero reference plane, typically known as ground, to keep as low an impedance profile as possible while still getting every part connected to it. The designer tried as much as possible to avoid routing traces through the ground plane. For every design with a ground plane, avoid touching or breaking up the plane as much as possible. This is to ensure minimum return path discontinuities, since it's a critical voltage reference for all components and signals. Let's analyze the impedance throughout traces in the design. The designer followed these principles, and now we see how the impedance profile turned out using impedance vision. Absolutely wonderful. The signals have been accommodated and the overall voltage and impedance profiles look great. And we see that in the impedance table as well, showing us that there are very few red spots, that is, high impedance areas. And this is great if you really want to get into more detail with precise numbers, and if you want to sort them. So you'll see that only some of the traces have a high impedance, and those are namely the ones that go over gaps in the PCB layout. Take care to have a low impedance on your zero reference or ground plane, and it will take care of the rest of your design. Next, let's look at the inner layers that carry our high-speed signal traces. There are some important signals needing our attention. The main microcontroller's S-clock signals, the transmission line is kept as short as it can while meandering for timing effects to avoid reflections as much as possible. But let's see if that actually worked. So we're going to add a pulse to this. And see how it performs. So since we do have some reflections, which can cause ringing on the signal trace, it will carry the voltage signals we want. However, it can cause some EMI issues if not contained. To deal with these kinds of issues, I've developed a certain methodology that I call DEPSI. DEPSI is short for Design for Manufacturing, EMI, Power integrity, and signal integrity. These are the four major pillars I use to base all foundational PCB design learning, education, knowledge, and review, solving any kind of issue on a printed circuit board. And part of the principle for DEPSI is that you don't want to sacrifice EMI for the sake of signal integrity. While the signal will get the job done, you want to use layer stackup to manage EMI caused by these reflected signals, in addition to terminations and whatnot. So with that said, let's look at the stackup. Looking at the inner layers, how the stackup is done affects electromagnetic interference, or EMI, which is one of the key pillars in the DEPSI framework. In this situation, it's appropriate to place this trace adjacent to a plane that can trap the EM waves being emitted by said trace ringing. And that's exactly what the designer does here. The trace is placed underneath or adjacent to the ground plane or layer 2. This traps any stray EMI waves and protects the top layer traces from crosstalk and coupling that could be caused by the internal signals. This also blocks outside signals from penetrating these more sensitive high-speed traces. But I want you to notice something with that being said. We understand that using planes adjacent to traces helps to shield other traces from EM waves. However, there is no such protection between layers 3 and 4. These are both signal layers carrying high-speed signals. So does that mean we might have a problem for layer 4 signals underneath layer 3. It would be a problem if you create opportunities for sensitive traces to couple their EM waves with each other. But we can avoid that by moving traces away from each other or routing them orthogonally to one another if they are on adjacent layers. And the engineers have done that here. For most of these traces, they are routed somewhat orthogonally to one another, and also areas that have high-speed traces, they are kept far away from other traces. This method is not as ideal as a whole reference plane shielding these two layers, but these techniques are still super effective. So that means we shouldn't have any signals underneath the S clock signals so that we don't have coupling or crosstalk between them in the first place. And guess what? We can see that that's what MAXIM did on layer 4. We see that there are no signal traces in this area underneath our high-speed signal traces. Smart. All right, there are some signals in layer 3 that have squiggly patterns. And we talked about this for a moment earlier. Why is this? Well, some signals need to go from a transmitter to a receiver within a certain time frame and within a specific time compared to other signal arrival times in order for that receiver chip to understand what's being transmitted. Given the fact that materials like signal traces, copper, and dielectric materials slow down the transmission and propagation of signals, we can use them to control when we want the signal information to arrive at the receiver pin. So we can meander the trace about the PCB to slow down and change the arrival time of the signal from transmitter to the receiver. You'll end up seeing squiggly lines to achieve this, and that's what the engineer did here. They wanted the time delays to match a specific arrival time, so to speak, for the main microcontroller. How do you determine the required time delay? There are two ways. You can calculate them yourself using various signal integrity methods and software, or you can check the manufacturer datasheets and design guides. I would recommend using the datasheet and design guides. It's much faster and most likely more accurate. In fact, this faster method is common practice because it just saves time and is likely more accurate anyway, even for senior PCB designers. But what if you did have to do these calculations on your own? Well, you would need to do the following. First, you'd need to calculate the required delay or timing for an acceptable signal timing mismatch for the microcontroller. Then use a combination of the IBIS model for the chip. Then understand the type of dielectric material to determine the signal propagation velocity and delay. Then, subsequently, with the signal timing for the traces, you can decide how much to delay the signal by. Like, say, adding a trombone or accordion style delay tuning method for the trace. But I still recommend asking the manufacturer for this information before trying to do all of that calculation alone. Then feel free to go ahead to still do your own calculations to verify your own methodology and seeing if you get similar results as the manufacturer for the device. There's one major thing though. This meandering process and all these signal integrity and high-speed techniques, they're only predictable if you have a strong control of the trace impedance and the PCB stackup with the right materials. You will need to have done the calculations for control impedance for your materials and PCB stackup beforehand in order for these techniques to work. Let's take a look at potential crosstalk. Crosstalk can be a huge problem for critical signals in your design because we don't want them to get the wrong information, especially at the wrong time. So we can do a crosstalk on coupling analysis. And when I check it for all of my nets, I want to make sure that
my coupling coefficient is 2% or less. Acceptable coupling for normal non-critical traces would be something like 8% or less, or 10% or less, depending on your design. But usually, ideally, I want 2% or less, especially on my most critical signals. Examples of such signals would be my communication signals and definitely my impedance control signals that need special timing when they arrive at the receiver. Now I can see which traces are at risk for having crosstalk caused by inductive coupling. Most of the traces seem to be fine. If I really want to get into the details and see what's at risk, I would go into my coupling table and double check some of these signals. Okay, that was a lot to talk about, but I think that covers layers 3 and 4. Now it's time to move on to layer 5. Now let's look at the power plane, which is just another voltage reference plane, just like ground, but it just has a higher voltage. In fact, ground really should be called a zero reference plane. Just as we designed for low impedance on the ground plane, the same must be done for this other voltage reference plane. If we have high impedance on this 1.8 volt plane, for example, any return path currents going through the plane could change its reference voltage to say 1.3 or 1.7 or 1.9 temporarily if we're not careful. First, let's immediately notice how the engineer tried to keep the reference plane continuous and therefore with a low impedance. Having a nice continuous plane giving us a low impedance also reduces potential noise and EMI. The less copper on this plane, the higher the inductive loop path that certain currents need to take, and therefore the higher impedance of the plane. All right, so that's all I have to say now for this design. I'll switch gears and talk a little bit about how to use existing circuitry in your designs. One of the main benefits of using reference designs is to design more efficiently, but this often comes with its own challenges, such as varying layer stackups and differing power specifications. How can you carry over the verified IP? What items do you need to watch out for when reusing circuitry in a new design? When you're reusing sections of your own design or some other design, you have to check data sheets for matching voltage levels just to make sure that it matches the devices you're using. You also need to watch out for current demands. Then you want to make sure that you make your traces wide enough because they may need to be different from the trace widths in the original reference design. Also, whenever you need to have controlled impedance traces like this design does, you want to make sure that your stackup accommodates the proper impedance for the traces you're using. If your stackup changes, which is likely to happen, and even if you're using a different manufacturer for the same stackup, the different manufacturer may be using different layer thicknesses for the copper and for the dielectric, which will affect your impedances. So you need to double check your impedances and make sure that you adjust your widths to maintain the ideal impedance for your design or even for the original design. You also need to take care of any special mounting configurations. Let's say your design is going into a different mechanical environment. Also double check placement when reusing design, placement of components. Cost can also be a factor. Let's say you're not able to do a 6-layer PCB in the amount of quantities that you would really want. So if you have limited quantity for manufacturing and you can only do 4 layers, then how do you redesign your reference design to accommodate fewer or more layers? Your routing strategy may need to change and need to figure out other ways to accommodate high speed or sensitive signals, especially clock signals. When incorporating any reference design into your own design, you have to consider the 4 fundamental foundations to any printed circuit board. That is design for excellence, which includes design for manufacturing, fabrication, cost, test, all of that. Then there's EMI, or electromagnetic emissions, or electromagnetic compatibility. Then there's power integrity. Will you adjust your power distribution network such that all your devices can get clean power? And finally, signal integrity in the DEPSI framework. All of these four fundamental pillars affect one another and will, depending on the needs of your design, these four fundamental pillars of all PCB designs drive how you update, change, modify, and use a reference design in your own PCB design.